As a physicist, are you curious to understand the physics of a spinning top? I am sure your answer is yes. So, let's get into it. A spinning top provides us with what is perhaps the most familiar example of the phenomenon shown in the given figure. That is, the lateral torque changes only the direction of the angular momentum and leaves the magnitude unchanged. This figure shows a top spinning about its axis. Let's assume that the bottom point of the top is fixed at the origin O of our inertial reference frame. So usually that is not the case. We know that the spinning top usually spins all over the place, but for simplicity we are going to make this assumption. As we saw in the video, the axis of this rapidly spinning top will move slowly about the vertical axis. This motion is called precession. Let's replace this top by a particle of mass m located at the center of mass of the top. Draw a position vector connecting the particle to the origin of our reference frame. The angle between the vertical axis and the position vector is theta. A downward force, that is, the gravitational force, acts on the particle. The magnitude of the gravitational force F is equal to mg. Because of this gravitational force, a torque acts on the particle. The direction of the torque can be determined using right hand rule. So that is R cross F. So this is the direction of the torque. Let's determine the perpendicular distance between the axis and the particle. So this distance is the radius of my precision circle. We know theta. So if we find sine theta, we will get, we know the sine theta is equal to opposite side by hypotenuse. Opposite side is the radius and hypotenuse is the magnitude of the position vector. So sine theta is equal to radius by the position vector r. So radius is equal to r sine theta. The mass of the particle is capital M and the torque can be written as R cross F. When we expand it, we will get Rf sin theta. We know the value of F, which is F is equal to mg. So when we substitute this value to this equation, we will get torque is equal to capital M g R sin theta. Let's analyze the effect of torque on the angular momentum. The direction of angular momentum is along the axis of the top. So from this we can see that the angular momentum and torque, they are at 90 degrees to each other. The change in angular momentum due to the torque is dl. And the effect of the torque is to change L to L plus dl vector. This vector L plus dl has the same magnitude as that of L but points in a slightly different direction. We know torque is equal to dl by dt. So the change in L, that is dl, is equal to torque into dt. So this is equation number 2. If the top has axial symmetry and if it rotates about its axis at high speed, then the angular momentum will be along the axis of the rotation of the top. But when L changes direction, axis also changes direction. The tip of the L vector and the axis of the top trace out a circle about the z-axis. This motion is called precession of the top. Let's determine the angular speed of this motion. In a time dt, this axis rotates through an angle of d phi. So, omega p is equal to d phi by dt. from the figure, it is clear that d phi is equal to dl by L sin theta. We know dl is equal to tau dt. So when we substitute this, we will get tau dt by L sin theta. So this is equation number 4. So let's substitute equation number 4 in equation 3, that is omega p is equal to tau dt by L sin theta divided by dt. This dt and dt will get cancelled out. So we will get tau by L sin theta. Let's substitute mgr sin theta for tau. So we will get mgr sin theta by L sin theta. So sin theta and sin theta will get cancelled out. So we will get mgr by L. This result implies that the precession speed is indirectly proportional to angular momentum. We know angular momentum L is equal to I omega. So this in turn implies that the precessional speed is indirectly proportional to rotational angular speed. So the faster the top spins, the slower it will precess. The frictional force will slow down the spinning of top. That is, due to friction, the rotational angular speed will decrease. So in turn, my omega p, that is my precessional speed, will increase. So let's derive a relation between torque and omega p. So we know omega p is equal to tau by L sin theta. So this gives us tau is equal to omega p L sin theta. And this can be written as tau vector is equal to omega p vector cross L vector. And the direction of omega p is along the z axis. There are actually two components to the angular momentum of the top. So one is rotational angular momentum about its symmetry axis, and another one is precessional angular momentum. And the total angular momentum is the sum of these two vectors. So this in general does not lie along the symmetry axis of the top. And initially we assumed that the symmetry axis of the top follows the direction of the angular momentum vector. But if the precessional angular momentum is much smaller than the rotational angular momentum of the top, there is only a small deviation between the direction of the symmetry axis and the direction of the angular momentum. And this small deviation causes a slight oscillation, and this is called as nutation. Nutation of the axis of the top back and forth about the precessional circle. So the axis of the top will have a slight oscillation because of this small deviation, that is because of this nutation. In nature, there are more examples for this precessional motion. Even our Earth is one of them. So you can do some search and you can find out many more examples for precessional motion.